Greetings. This is a presentation of our thesis project, an automated monitoring and management system for aquaculture applications. The Philippines has a growing aquaculture industry, mainly producing fish, shellfish, and to a lesser degree, seaweed. Seaweed farming plays an important role in the aquaculture business and is constantly growing. Seaweed is considered to be the second largest aquaculture farming industry in the world. Water quality monitoring is important in maintaining healthy and productive aquaculture. However, conventional methods of water monitoring brings about problems such as human fallibility, excessive time resources, logistics, and limited accessibility. In recent years, systems have been developed to resolve most of the mentioned issues through automation and with the use of new technology and concepts. These existing systems, however, present problems of their own, such as a lack of salinity and turbidity parametric sensors, a dependency on wired internet connection, the involvement of excess human intervention, restriction by physical cable connections, and a lack of environmental exposure protection. The general goal of this study was the development of a water quality monitoring and management system for aquaculture applications that addresses the prevailing problems of existing systems and methods. The objectives were: first, to establish a base station for data processing, instruction, and control over the system. Second was to develop a sensor node that gathers water parameters. Third was to develop an automation node that controls the automatic water management processes. Fourth was to integrate an IoT system through wireless communication between the nodes and the base station, as well as establishing connection to the internet. Fifth was to develop a web application for remote monitoring and control over the system. The project covered a water monitoring and management system for land-based aquaculture set up in a controlled environment. The system had 3 sensor nodes, 2 of which are simulation node and 1 automation node. The system uses wireless communication through XBee modules using the Zigbee protocol. Who will benefit? We have aquaculture business owners, aquaculture personnel and employees, hobbyists and enthusiasts, and for general water quality monitoring purposes. The system does not cover changes in water condition, water quality discrepancy. It is range dependent. It would only be able to measure pH, salinity, turbidity, water level, and temperature. Only 3 sensor nodes was deployed, 2 of which are simulated nodes. Only 1 automation node was constructed. Human intervention was needed to initialize the system. A loss of connection ceases the system. The system is unable to detect faulty components and does not have any backup power. This is the system overview. The system is composed of 3 subsystems: the base station, the sensor nodes, and the automation node. The base station processes the data and uploads them to the server, which is accessed through the website. The sensor node gathers parametric data and transmits them to the base station. The automation node intervenes if there are any abnormalities detected by the system. The sensor node is composed of an XBee S2C module and the parametric sensors. The sensor node has a one-way communication with the base station. The gathered data from the sensor nodes will be stored locally at the base station and remotely by the PHP MyAdmin database. For the scale and needs of the project, the star topology was chosen due to its ease of implementation, and should one end device fail, the connection with other components to the base station will not get disrupted nor severed. This is the login page of the website monitormyseaweed.com. This is the data dashboard page where data is presented along with its timestamps. This is the graphs page where data is represented in a line graph. This is the automation node. It is composed of an XBee S2C module, a heater, an aerator, and 2 solenoid valves for both water in and out. There were 7 tests that were conducted, first of which was the sensor calibration testing. Each sensor underwent a calibration process corresponding to their requirements in order to ensure reading accuracy. The pH and salinity sensors were calibrated using buffer solutions with indicated values used as reference. The temperature sensor was calibrated using water at 100 degrees Celsius or at boiling point. The turbidity sensor was calibrated using clear water with an expected output of 0 NTU. The water level sensor was calibrated using a steel tape measure used as reference. The results of the calibration testing shows that the values acquired by the sensor in comparison with that of the reference values from buffer solutions and readings taken from analog instruments are within approximate range with minor differences. Next test was the reading validation test. Analog instruments were used as validation reference for water level and temperature parameters. For the three remaining parameters, a mixture sample of coffee and salt was given to the USC Water Laboratory to be tested for pH, turbidity, and salinity. The reading outputs were expected to be approximately the same with the results taken from the laboratory. This is the result of the sensor node readings. Each test sequence composed of 30 different data readings, averaged out. 10 test instances were conducted and their average were taken. The salinity parameter had the largest error at 7.95%. One contribution to the discrepancy in salinity readings is due to its correlation with room temperature. When water temperature is hotter, water molecules will slightly expand, causing salinity levels to drop. Inversely, when water temperature is cooler, salinity levels will slightly increase. The duration of the test where salinity levels were acquired lasted approximately 8 hours, during of which room temperature where the sample was stored varied throughout the day, causing irregularities. The remaining parametric sensors met the expected error output of less than 5%. One factor that affected the accuracy of the turbidity sensor is how susceptible it is to the change of the brightness in its environment, the inconsistency causing irregularities in reading. pH readings are affected by the half-life of the solution that is being sampled. Over time, the concentration of the solution will decrease, in this case, the coffee mixture. Towards the end of the test, the acidity of the mixture slightly neutralized, hence the average pH level reading taken by the sensor is slightly higher. Since water level could not be verified through laboratory testing, an analog instrument was used, a steel tape measure. Human error likely contributed to the difference between the readings taken by the sensor and the readings taken from the steel tape measure, which was done through visual observation only. Temperature was also a parameter not verified through a laboratory. An alcohol thermometer was used as reference to compare the readings taken by the sensor. Human error was also expected when taking measurements through the alcohol thermometer, as level indicators were incremented only by quarters, resulting in lesser accuracy. Next test is the XB communication test. This test covered the operational range between XB modules. 10-meter distance increments were added after each successful test instance. The max range for outdoor scenarios with clear line of sight is 120 meters. For indoor scenarios with obstacles and other interferences, it is only at 30 meters. Next test is the base station testing. This test determined whether the base station can receive and send data to the database, receive data from the sensors, and send instructions to the automation node. The base station was able to upload data to the phpMyAdmin database, which was then presented on the web application through the dashboard and graphs pages. The base station was able to receive data from the sensor nodes transmitted by the XB modules and received by an XB module connected to the base station, which was set up to be the coordinator. Upload times varied throughout the day, with early mornings and late night times experiencing the fastest upload speeds at approximately 1 second. During internet peak hours, upload times would take approximately 3 to 5 seconds. Next test is the automated intervention testing. This tested the base station's manual and automatic control of the devices on the automation node. Base station had an auto feature in which, upon reaching certain sensor thresholds, would turn on or off certain automation devices in the automation node. These automation devices were connected to a relay switch, which controls which components should be turned on or off by providing or cutting off power. The relay switch would take approximately 1 second to switch from on or off and vice versa. The tank and drain valves had the longest delay due to the solenoid valves used taking approximately 3 seconds to fully open or close. Next was the web application and server connection testing. Web application was tested if it can perform remote operations such as monitor data, adjusting threshold values, and send override commands. The data accumulated by the base station and data received by the server was compared and expected to have the same data. The same data value will be observed across different access points, except in the graphs page, as data values was set up to be rounded to the nearest ones place. The last test was the end-device connection testing. This is a testing of devices such as laptops or smartphones to access the system through their own browsers. Also, the capability for the web application to be accessed from locations outside of the Philippines was simulated using VPN networks. The web application was accessible through computer units as well as mobile devices. The web application's functions, actions, and commands proved to be functional. The website was also be able to be accessed from foreign locations simulated using VPNs. The login, graphs, threshold, and logout pages experienced the least loading times at 3 seconds. The dashboard page had the longest loading time because of the number of data assets it had to display. The main goal of the study of developing a monitoring and management system for the use of aquaculture purposes were met. Problems brought about through conventional methods of water monitoring and management were addressed through the integration of an IoT system where digital instruments were implemented. Water monitoring and management devices were automated and can be controlled wirelessly and remotely through the development of a web application as well as a local base station. Data gathered from the digital sensor is within range with the data taken from the USC Water Laboratory. Human error in maintaining a fully controlled environment accounted for virtually all the errors the system had experienced. Upon further study and examination, these are the following recommendations. First is the improvement of the controlled environment setup. Second is to upgrade XB modules to that of higher range versions. Third is to equip simulation nodes with actual sensors. Fourth is to construct an automation node per sensor node. Fifth is to develop an alert system for faulty components. Sixth is to use a real-time platform such as Firebase for web development as well as implement website responsiveness. Seventh is the soldering of wired connection to prevent being loosened over time. That would be all for our presentation. Thank you.